Okay, so today we are starting igneous rocks, and igneous rocks are the first of the three rocks that we talk about. They kind of were where we started in the rock cycle, and with good reason, as you saw. This semester we've already done them in lab, so you guys are familiar with some of the names already. You might even be able to picture one or two of them. Remember, in here, when we're doing igneous rocks or sedimentary rocks or metamorphic rocks, I'm never going to expect you to recognize a hunk of something. Okay, I know I said that the other day, but I can't say it enough because I still get asked, which is fine. Ask questions. I'm not saying that. But yeah, okay, and here we'll talk about what it means to be basalt instead of just, oh, that is a hunk of basalt, and so on and so forth. So our focus is there. I know the big thing these days is to say I was today years old when I found this out. I am a little embarrassed to say how late it was in my career that I made the connection between igneous and ignite, IGN, there at least in the beginning. But yeah, igneous, fire. Go figure. I imagine, going way, way back when we were still young and learning about our planet that, the earth cracking open and magma coming out, lava coming out was just mind-bogglingly amazing, to folks to see. We know what it is nowadays, and it's still a sight to behold. But you can certainly see myths and legends being born out of this stuff, and giant mountains that would occasionally shake and sputter and send this stuff coming down the sides. So, igneous rocks do, again, as we said, have their origin in... Spacebar isn't working this today, and I don't know why. Have their origin... Oh, yeah, I was supposed to have that on while I was talking. Pretty, isn't it? I think so. Igneous rocks have their origin in either lavas or magmas. We'll talk about this more in depth, but again, they're essentially the same stuff, just when they're at the surface, we call them one thing. When it's inside the earth, we refer to it as something else. I think primarily just to confuse, 101 students. The main reason. You see the hot flow there in the center, and then off to the sides where it is darker, that's where it started to cool off. You probably figured that out, but nonetheless. All right, smarty pants. See, on here, I never go to full screen. I go to some variation on it, but that's exactly why it's not working. Thank you. Yeah, see, I still get presentation mode, so it looks a little different, but I'm used to seeing slides on the side, so when I'm groggy like today, that is projecting very pretty. It looks like a stained glass window almost. That'd be a cool window. It's a little too much black for a stained glass window, but nonetheless. Hey, spacebar's working. So, at any rate, this is where we need to make the connection. And in lab, again, we go straight from minerals to igneous rocks, and I make a big stink about you guys not remembering the colors. I do that for a couple reasons. One, to hopefully scare you into studying for the mineral test. Oh my God, you don't know what the pink stuff is? You don't know what the white stuff is? But also because we don't really talk about the formation of minerals when we do minerals. All right, and I don't know that I ever will, but here now, in igneous, when we talk about these rocks growing out of a lava, I'm going to quit saying magma or lava, I'm just going to pick one, okay? When we talk about rocks growing out of a lava, well, if you think about something like granite that was orthoclase, albite, quartz, biotite, and I think some hornblende thrown in there. Trying to remember that You'll see the diagram again, but trying to remember that diagram we had in the lab books. Those crystals don't just, crystals of orthoclase are all by there, they don't just appear, okay? They had to form, they had to grow. Well, that's what we're going to be talking about today, okay? And, this really does go back to the formulas, which I never had you memorize, but again, we want to acknowledge that there's formulas there. And that formula is a recipe, nothing more. Tells us that we need to have silicon and oxygen and aluminum and so on and so forth. And that's how you make orthoclase, and that's how you make albite, and those assemblages are what we call, as I said in lab, kind of arbitrarily, what we call these rocks. All right, so I don't want to get too deep too fast. So lava and magma, this is that molten mineral mixture, okay? I sometimes call it elemental stew as well. Because it's composed of elements. It's soup. It's not orthoclase and albite and quartz. It's silicon and oxygen and aluminum and iron and whatever else. Sodium and potassium. And if you didn't already have the magma versus lava, it's down there at the bottom, but we talked about that, I think, 3 times already. All right, so while we had, igneous is kind of confusing because we tell you there's 2 types of rocks, intrusive and extrusive. And then we say there's 3 types of rocks, the chemistries, the felsic, intermediate, and mafic. That's both true. Right now we're going to talk about the 2 categories of rocks based on where they are formed, where they're made, okay? And from that, we have the intrusive, and that was sort of the lead up on this previous slide here. I didn't use the words yet. But magma is inside the earth, lava's at the surface of the earth. So when we're talking about magma, we're going to talk about intrusive igneous rocks. So they crystallize inside the earth. They form from magma. Again, this is getting redundant. Because of that, they're inside the earth. They cool very slowly. All right. And as I may have said, this is sounding kind of familiar in my brain. I may have said during the rock cycle conversation, this might seem counterintuitive to you because these are the guys that end up having the large crystals, coarse-grained igneous rocks. And it's kind of like if you've ever had a garden or you know someone who's had a garden and you have to wait for the vegetables to grow. The longer they are able to sit in that garden, the bigger they get. So it's really not counterintuitive at all. The longer that this stuff stays semi-molten, the bigger those crystals can get. It depends, I guess, on how you attack it. If you think about the crystal as the finished product, you can say that if it takes a really, really, really long time, well, maybe it's not getting very big, and so on and so forth. But it literally, the longer it can cool, the bigger it can get. Now, there's a word that they use for this called phaneritic, and I've really never used it. I'm trying over the last 3, 4, 5 years to use the formal words for it. We're in 101. This is an introduction class. You guys have enough vocabulary as it stands. Okay? So coarse-grained, fine-grained, mixed-grained, it's always sort of served its purpose. But I am introducing the proper terms. So phaneritic. Phanero means visible. So remember back, these are the ones where you can see the different colors. You can see the crystals then. So that's the coarse grain. There's the connection there. Now, I will never say plutonic rocks. Plutons are large pools of magma underneath the surface of the earth that either can feed volcanoes or crystallize themselves into rock. There's a Pluto, god of the underworld kind of thing, not Mickey's dog. But I don't ever use that word. But phaneritic, I should use. There's a handful. They might look familiar to you. Okay, we have our friend granite and diorite Dalmatian there, and then gabbro. Don't worry about the felsic intermediate mafic yet, but that's just a hint. Remember I said there's 2 ways, and then there's 3 ways to classify them. Well, that's going chemical-wise, and that is conversationally coming up soon. So the extrusive igneous rocks, extrusive, external, extrude. All right, we got that ext showing up over and over again. These are guys that form at the surface of the earth. So therefore, they form from what we call lava. By comparison, they cool very, very quickly. So the crystals don't grow very big. The word for that one, the formal word for that one, is aphanitic. Remember, our prefix a means not, right? So they're not visible. Phanero means visible, so a, not visible. And again, these were your fine-grained rocks, and you might remember, you're going to see rhyolite in a moment here, okay? Remember, rhyolite was the same stuff as granite, but you took all those colors that were in granite and sort of blended them in on that artist's palette together to make one pinkish grayish color. And that's because the crystals are so small you can't really see them. And again, these are the guys that come out of volcanoes or volcanic eruptions. Just like I don't say plutonic, I seldom say the word volcanic. And then there's 3 extrusive igneous rocks. We have rhyolite that I just talked about. Looks a little grayer here than it. The one on the board kind of looks pink. On my screen, it's kind of grayish. Yeah. But ours were a good bit pinker. The andesite, you guys had the porphyritic andesite with the great big black crystals in it. Remember that? And then basalt. This basalt looks a good bit coarser than ours as well, but dang it all, these were the best pictures I could find. So intrusive and extrusive. In lab, we mentioned that there was another kind of grainy texture, and that was the mixed grain, porphyrism. And what happens is, if you want to sort of follow along mentally, right? We told you that magma can eventually work its way to the surface in a volcanic event and make an extrusive rock instead of an intrusive rock. Well, what happens with porphyrism is that the magma actually stays in the earth long enough at a slightly cooler place that some minerals do start to crystallize. And when that lava comes out, it's actually got these little mineral crystals floating in it already. Well, once it hits the surface, that lava cools very, very quickly, again by comparison. And so you end up with a fine-grained rock with these large crystals suspended in it. Hence the chocolate chip cookie rock that I refer to it as. The large crystals are called porphyrs. And now this might look familiar. This is the rock, at least that we have. There's other kinds of porphyritic rocks out there. Okay. You could arguably have a porphyritic rhyolite. You could have a porphyritic basalt, I suppose, and so on and so forth. But we just have the andesite. And as I said, that is the only andesite I have. I do not have any non-porphyritic andesites. All right, so I've indicated a couple times already, even though I've given this lecture, I don't know, 75 times, who knows how many, 100 times. I still do it a little bit differently every time I give it, which I suppose is a good thing, at least for my brain. So I made a big stink about we classify them in 2 ways, we classify them in 3 ways. This is where I usually introduce that at, okay? So we just discussed one of the two ways that we classify igneous rocks, and that's by texture or grain size. Now we're going to take some time to talk about classifying them by their mineralogical composition, all right, or their chemistries, as I say. And actually, what I say much more frequently is their flavors. I'd like to think that if we ate rocks, that they, a granite would taste different than a gabbro, for example. They've got entirely different ingredients in them. So different flavors of igneous rocks. I don't know, that slide's out of order seemingly, because I'm talking still about textures. That's weird. I'll move that slide later, though. So to summarize, before we move on to talk about the flavors, we have phaneritic, which is the coarse grain. We have aphanitic, which are the fine grained. We have the porphyritic, which are the mixed grained. And then we have vesicular and glassy. Vesicular rocks contained vesicles, which are little pores, little pockets. Lava is chock full of gas, so when it comes to the surface, it bubbles out, kind of like when you pour yourself a glass of pop. I'm in New York State, I shouldn't call it pop, but you know what I mean. Glassy, on the other hand, those rocks cool so quickly, typically because they end up in water, but they cool so quickly that they don't have even a moment to grow crystals. Just like glass in our windows here is non-crystalline. Igneous rocks that are glassy, hopefully obsidian comes to mind for you, okay? And you're going to see a little paragraph in your book about this. The igneous petrologists, those that study igneous rocks, just really, this is an oddity for them. Since there are no crystals present, technically speaking, there are no minerals present, right? Because remember, definition of a mineral, naturally occurring, inorganic, crystalline. So we don't talk about obsidian containing quartz. We talk about obsidian having silica. Same side of the coin, different sides of the same coin, but technically correct nonetheless. The same is true for vesicular. That's just basically frothy glass. And that was the reason that the vesicular and the glassy did not appear on your table in the lab book. And also when we get to see that table again here in a couple minutes when we talk about the chemistries, why you're still just going to see the same 6 rocks, not the 2 vesicular or the glassy. And we have a nice little summary slide here. Starting in the upper left, we go from our phaneritic, our coarse grain, to our aphanitic, the fine grain, to the porphyritic, the mixed grain, to that is supposed to be pores or vesicles you see in there. It looks like a hunk of scoria on the bottom left. And then in lab, I told you that obsidian can be some other colors than just black. This one has a couple colors in it. It's pretty stuff. Okay, let me just move that slide because I have a feeling I said the same thing last semester and never moved it. No, not going to let me move it. Can I go up? I could go up. All right, so, anywho. So igneous petrologists or igneous rock people, scientists classify the rocks based on 2 things: texture, which we've just finished talking about, and mineralogical composition, which we're going to start talking about now. All right, so felsic intermediate mafic. You heard me say these words a handful of times. Again, this semester we've done igneous rocks in lab already. So you are familiar with these because of that. You made 3 columns of rocks, okay, based on, you might remember, their minerals that were found in them. We told you, generically speaking, felsic rocks were light-colored, mafic rocks were dark-colored. Remember all that stuff? And intermediate was, of course, a mix. And this is very similar to what you saw in your lab books. You have your 6 rocks across the top. We'll politely ignore peridotite for the moment. Peridotite is essentially a hunk of olivine. More than likely, our olivine mineral specimen that we had in class is peridotite. But you see the 6 rocks that we talked about. Below them, you see some arrows that are trying to show us chemistry, increasing contents of certain important minerals. On your lab book, the only one I really left was the first arrow there, the silica arrow, where we talked about increasing silica content. But the more involved diagrams show us that, what was K and Na? Who remembers? Let's involve you guys a little bit here. And how about Na then? So we got potassium and sodium at any rate, okay, which increase towards felsicness. And yes, K for bananas. Lots of potassium there. And then as we go towards maficness, we see calcium and iron and magnesium that increase as we go in that direction. And it's not like there's some mad scientist adding these ingredients. It's a premix, right? You get what you get in these magma pools and these lava flows and whatever you want to make your rocks out of. Mother Nature makes these chemistries, these magmas, and this is again our categorization. What we've come to realize that they're composed more of or less of. If for some reason we found ourselves in a position where we wanted to make granite, you would set those dials on that weird picture, some mad scientist movie that you saw, and they'd be setting those dials on their crazy machine to increase the silica and decrease the calcium and iron and magnesium and so on and so forth. Another big difference here is that we've got the felsic intermediate mafic across the bottom on this table. This introduces the word silicic as well. All right. Another word for felsic is silicic, is silica rich. I tend not to say silicic. It sounds a little naughty to me somehow. I don't know why. But so felsic. All right. But they are silica rich minerals. Just like at the very end, we have this ultramafic, and that's where we stick our peridotite at. Again, if this were an igneous rocks class, we would definitely talk about ultramafic. I've always thought they should have an ultrafelsic, though, because that really helps explain obsidian's presence. Okay, being 99% silica. But I don't recall ever seeing an ultrafelsic. So I'm sure the folks in charge have a very good reason for that. But it is essentially just straight silica. So one more notch ought to do that. You see our familiar friends, the minerals in here. All right, and again, they didn't use the Geology 101 mineral terms for whatever reason. So instead of orthoclase, we see sodium-rich plagioclase. Instead of albite, we see potassium feldspar, but that's what they are. And we see the quartz. Instead of this one actually is missing a little bit of stuff. We see the pyroxene here. This is the hornblende is missing in this diagram, but Well, yeah, but it's over here, and this is and this is also inverted, by the way. You guys might have noticed when I did quartz last. Okay, on your diagrams, quartz was up here. It all works out the same in the end. But on ours, we do have a potential for both pyroxene and augite to, hornblende and augite to show up in your gabbros. They're emphasizing more of this plagioclase spectrum, the feldspar swirl that goes across the center of our table. Yeah, why do you know that about amphibole? I see. You didn't get that out of our lab book. I don't think I call it that. It's fine. You're allowed to go out into the World Wide Web. I just wondered where you found that one at. All right. So, lava and magma. Again, if you couldn't figure it out, you're going to see a lot of questions surrounding this because, believe it or not, sometimes folks do have trouble sorting this all out. Where we use lava, where we use magma, and what grain size it ends up giving you these things. Why is this here again? I guess we're just reminding you. Just reminding you. So often I feel like somebody sneaks into my computer and messes with my PowerPoints. So, felsic intermediate mafic. Yeah, that really is the true order here. This one a lot more resembles what you guys had in lab. Brings it together just a little more inclusively. We've got the intrusive coarse grain, extrusive fine grain. We've got our quartz where we expected to see it. Granodiorite. How about that one, huh? And dacite. We didn't talk about those guys. But diorite and andesite, here we are. So, and remember you had that tiny little bit of quartz that snuck into our intermediate as well. And here is the amphibole. The hornblende. Yeah, it really doesn't blend on this one either. I may have to take that into consideration at some point. I doubt they changed these charts after so long, but all right. Now to the serious stuff. So, remember we're growing rocks out of magma or lava. We're crystallizing. And it's not that it's hard to visualize this, but the majority of the things that you're familiar with in life, we're trying to melt. We crystallize very few things. Water is about it. Right? We make ice cubes. But everything else, you're melting butter, you're melting chocolate, we never talk about crystallizing. And what we want to keep in mind is that they are essentially a knife blade. And there is just a teeny tiny point at which we stop doing one thing and we start doing the other. Now, before we get into that, all right, I want to also point out that not all rocks melt the same. Again, going back to what we've melted stuff in our kitchens, it might be a lot easier to melt butter, say, than it is to melt a hunk of chocolate, or you might feel the opposite is true, whatever. Not everything works at the same temperature. So just as an example, I'm never going to ask you these numbers. I want to point out that granite, okay, melts at 625 degrees Celsius. It's in Celsius, not real helpful to most of you, but basalt, over 1,000 degrees. I remember one of those is felsic, one of those is mafic. Maybe there's some brash generalization we could make there. But at the moment, we're just introducing the idea that two rocks, have really completely different melting temperatures. So, an easy question. If you were to throw, and just let's pretend this fire can get as hot as it needs to be. If you were to throw a hunk of granite and a hunk of basalt into a bonfire, which one would melt first? Granite? We could all agree to that, right? Okay. Let's say you had a cauldron on top of that bonfire full of magma, lava, elements. Which of these rocks would start to grow first if you turn off the fire? Why? No, not because it's mafic. It's not that they cool quicker. It's that what number are you going to hit first if you're cooling down? You're going to hit the 1,000 before you hit the 600. So while it was the first thing to melt, it's the last thing to crystallize. And while basalt was the last thing to melt, again, if we're at this, and I may have set it up wrong. You guys weren't on you understand the idea, but you didn't get where I was going with it. Again, we're hotter than 1,000 degrees in this cauldron. As that cools off, the first thing that is going to start to grow is the basalt, because we're going to hit that temperature first. All right. So, this is not the best slide to have a fancy background on. So water freezes. I just slipped down my stairs this morning, which is why I'd like to think that I'm a little hazy as I'm talking to you here. I don't think I hit my head though. But water freezes at what temperature? 32 degrees. Ice melts at what temperature? Melts. No. Well, if it freezes at 32, it can't melt at 32. Again, I'm nitpicking, but so we got a decimal, right, in there somewhere. And how far out do you take the decimal? Is it 32.1? Is it 32.09? So on and so forth. But I'm talking about that knife blade again. We're right there. On one side, it's crystallizing. On the other side, it's melting. Okay. So while we say that granite melts at 625, granite crystallizes at what? Well, at least 624. If not 624.9999999999999. So they're very similar points. And just one side of one is the other. So, believe it or not, we had a guy, probably a handful of people, but as always, one of them gets the credit. Mr. Bowen, who sat there and watched lava cool. We're going to assume it was lava since he didn't go inside the earth, probably. And what he realized was that in the end there is a predictability to this. If you had, again, our three sort of generic flavors of lava, our felsic, our intermediate, our mafic, think of them as your chocolate, vanilla, and strawberry of ice creams, okay? And again, had to be some insight in here to realize that that different lavas grew different types of minerals, i.e. different types of rocks in the first place. We won't even, get into that. But he recognized that there were three basic compositions, and he must have sat there and watched them cool. Kind of a fun job, I suppose. Read a good book while you're doing this or something. At any rate, he realized that time after time again, if you had a felsic lava, that this, that, and the other thing would form in that order every time. If you had a mafic lava, that this, that, and the other thing would form in this predictable order every stinking time. And it is tied to, that crystallization and that cooling thing that we just talked about. Because remember, we're starting at a high temperature and we're going down. So what is the first thing to crystallize? What is the last thing to crystallize? And all I was trying to make us think about earlier was that we talked about melting a rock. Okay, that last thing to crystallize is going to be the first part of that rock to melt. Now, the stuff you have in your kitchen, again, is pretty homogenized, right? All that butter is going to all melt at the same time, more or less. But there's always that little bit that doesn't melt, right? You can kind of think of it that way. So different parts of that butter are melting at different rates and so on and so forth. Same is true in the opposite direction. Some parts of that rock are going to crystallize before others. Remember the porphyritic rock? We had those big black pretty crystals. That must be something near the top of the list. So this is kind of what I just said. Give you a second to absorb it. All right. When we show you Bowen's reaction series, there's two different things going on. I don't make a big stink about this. We're going to acknowledge that they exist. We do talk about them, but I don't, at a testing level, I don't ever say the continuous branch or the discontinuous branch. But I do want to, and you guys will see, you say, oh yeah, I know what he's talking about. I remember the feldspar thing. The continuous branch is that feldspar swatch that went across the whole table. It blends. There's like 500 feldspars because of that. But the discontinuous branch, that's the one that gives you your very distinct minerals. You'll see. But again, we're using the proper words, but I'm not going to test you at that level. All right, here she be. So, just again, and then we'll never mention the words again. On the left side here, you see how we make one thing, then we stop, and we start making another thing, and then we stop. That's the discontinuous one. Okay. On the other side, where we just have that big long black to gray to white arrow, that's the continuous one. And it's a spectrum. There is no dashed lines when you stop being one feldspar and you start being another. The mineralogists, again, love, if they get into that kind of stuff, they love the heck out of their feldspars. And they dissect them, bisect them like crazy. So we're going to talk about the left side for now. And I'm just going to make up a number. Again, the temperatures are not something that we need to worry about. We need temperatures, but we don't need specific numbers for you to memorize. So we're just going to say that this pool of magma that we have right now is 5,000 degrees. Okay? We're not going to say Fahrenheit or Celsius. We're just going to say 5,000 degrees. And it is full of elements. What elements? Well, go back to your lab book, find all those formulas for all those minerals that are in there, and write a list of ingredients. We're making cookies. Okay? You need silicon and oxygen, obviously. You're going to need some aluminum, some iron, probably some calcium in there. And you got this batter already made. This is a closed system. So anywho, you got all those elements sitting there floating around in this molten mineral mixture, this elemental stew, and it starts to cool off. Why does it start to cool off? Well, it's moved away from its heat source. May have come all the way to the surface as lava, may just have gone up farther in the crust and we still call it magma. Doesn't matter. We're cooling off. The first thing to start growing, according to Mr. Bowen, is olivine. What's in olivine? Yeah, I don't remember either, but you know there's stuff in olivine, right? Silicon, oxygen, iron, whatever. So as olivine's growing, it's plucking that stuff out. It is no longer floating around in that stew. We're locking it up and making crystals of olivine. Then when we get down to, what did we start at, 1,000 or 5,000? I forget. 5,000, all right? So now we're going to get down to 4,000 degrees. We actually stop making olivine, and we start growing pyroxene, which is augite. What's in augite? Again, whatever's in augite is in augite. More silicon and oxygen. These are all silicates, right? Look at it. Those are all silicates. So you're going to have silicon and oxygen. Again, probably some iron. It's dark stuff. Remember, our augite is dark. You're taking that stuff out of the mixture. You're making that batch of cookies and setting it aside. We're doing a bake sale. We're going to make a whole bunch of different cookies. Now, of course, you're not setting it aside. It's literally growing next to that olivine, right? It's crystallizing all around it. Picture trying to make something that looks like, granite. We're on the wrong side of the table to make granite, but you can picture granite, right? The pink, the white, the crystal, So we just grew some olivine. Now we're growing some black stuff around it. Then we're now down to 3,000 degrees. We stop making pyroxene. We start making amphibole, the hornblende. Slightly different ingredients. But let's say, for some strange reason, we'll save this for biotite. Now you're down to 2,000 degrees. It's time to stop making hornblende. It's time to make biotite. But let's say, for whatever reason, this mixture you just made, you're out of iron. Does it make biotite without iron? No, because for one thing, that wouldn't be biotite. It would, if it existed, it would be some other thing. It doesn't actually crystallize anything at this point. It sits there, which I think is kind of weird. You would think it would maybe, like I said, make an ironless biotite or some new funky mineral. But for whatever reason, if you run out of an ingredient, it doesn't make anything in that temperature range for crystallization purposes, I'm guessing. But so it sits there. And then at some point, we get down even cooler. And we start making, remember the potassium feldspars, your orthoclase. And guess what's the last thing to form? The simplest thing, the quartz. It's just silicon and oxygen. Now, let's say you still have the opposite end of the spectrum. Let's say you still have some iron left. What happens to that at that temperature? Well, it probably crystallized out of the mixture a ways back, and you just got some random iron flakes here or there. And you guys are like, do I have to look at this black stuff in this white rock? Remember those questions? Well, no, it's just an impurity. Don't worry about it. There's your impurity. To the other side for a minute. So the feldspars, there's no solid black line. It blends from one to another. And like I said, the folks that study these really just get into splitting them into all these different minerals. Okay, this one's unique enough from the one before. Let's give it a new name, and that's fine. Bless their hearts, they enjoy that stuff. But we talked about how on the felsic side it was albite. On the mafic side it was that dark feldspar that was kind of like labradorite but didn't shine blue at us. Okay, and in between I kind of lied to you. And I said that it was a little bit of albite, a little bit of that dark stuff, and it helped you make that speckled diorite Dalmatian rock. There's a lot of other feldspars in between that stuff, okay? But at this level, we don't care. So, I said that we were on the wrong side of the table to make granite. So you see over on the side, you got the mafic, the intermediate, and the silicic. This is actually that same table we've been looking at, that same table that's in your lab book. You take the bottom right corner, over there where silicic is, and you flip it over to the upper left-hand corner. That puts silicic or felsic in the upper left. It puts mafic in the upper right, where it kind of already is. And that makes the table we've been staring at. I think I put one here. No, I didn't. So, I intended to put one there so I could see. See what I'm trying to show you? So what I'm saying is you take this corner down here, you put it up here where the word olivine is, and you've got your quartz, your orthoclase, get some muscovite thrown in there for good measure, your biotite, your hornblende. And then you've got on the other side, you've got your olivine, you've got your dark feldspars. It works out, just trust me. So they're connected. I think this one came first. And then we realized for identification purposes, it's easier to, look at it in the other direction. Who knows what they decided 200 years ago, but. So, Bowen's reaction series. What do you need to pull out of this? What you need to pull out of this is, certainly I'm never going to have you fill in this chart or anything like that. What we want to get out of this is the idea that different minerals crystallize at different temperatures. And once you use up something, you can't make the next thing that needs it. And that's what gives us our variation, why somebody's diorite looked different than the group next to theirs' diorite. It was still diorite, okay? But whether it stayed at a certain temperature longer or we ran out of an ingredient, that explains the variation, the diversity that we see in all these things. They have the correct elements to qualify as a diorite, but percentages, again, we'll go back to the cookies thing or the brownies thing. Hey, it's a brownie, it's a brownie, it's a brownie. But you know what? Some people's brownies taste better than other people's brownies. How come? Oh, well, I put this special ingredient in my grandmother. It's always done. Or I always buy these chips. I use dark chocolate instead of milk chocolate. Whatever. It's still a brownie. But there's these little variations in it that make them all different. Same is true with rocks. All right. And again, these are our tables. Mother Nature can do whatever the hell she wants to, and quite often plots outside of our tables. But by far, these count for, the majority of what we come across. This is us staring at rocks for 200 years and saying, I think this makes sense. You guys agree? Yeah? Okay. Let's publish it. So, that's what a lot of science is. All right, so that's it for really the nitty-gritty on how igneous rocks are made. Okay, we talked about how they crystallize. We talked about the ingredients that go into it. Your book is going to go a little further in some directions than we did, but I shadowed it pretty close, or at least the semester that we used the semester I wrote this lecture. But you can only say so many things about igneous rocks in a 100 level course. So they're all fairly simple. But before we move on, any questions about how we put together an igneous rock? All right, so as we said, there's two kinds of igneous rocks. There's intrusive and extrusive. Extrusive leads us to the volcanoes chapter, which we're going to do next. Okay. Intrusive isn't all that exciting. Again, I'm sure there's an entire semester course for it at the 300 or 400 level for folks that want to go into that kind of stuff. But at this point, we just need to talk a little bit about a couple of things and leave, as I said, the extrusive for the next chapter. So, igneous intrusions. This is narrative. I wouldn't write it all down if I were you. So, in order to cool off, we already discussed that magma needs to work its way up towards the crust. You're farther away from the heat source, right? The Earth is old. It's cracked. And so the magma works through these little cracks like water through pipes. It intrudes. Intrusive igneous rock. See, they're clever, aren't they? They have classified intrusions into three main categories. Dikes and sills, which think of as the pipes for a moment. And then Pluton, which is like a pool. It's that giant puddle that we mentioned a little while ago that feeds these pipeworks. And yes, arguably these are the same pipeworks that could lead to the surface to make a volcano, but these aren't in this conversation. They're going to stay inside the Earth. Now, I call these pipes very loosely. You do it because it's easy to picture then, these little cracks. But if you think about, something that has cracked, if you've come across anything that's cracked in your life, quite typically they're not two-dimensional. It's kind of a long thing. All right, it goes, a piece of wood cracks. It goes all the way through. So these aren't pipes so much as, much deeper. I don't know what other word to use. That's the other reason I haven't done it. But they're not often narrow little tubes, okay? But for our drawings, for our conversations, when we get to a picture, I'll try to explain better. So, dikes and sills first. Those are the big ones. Plutons are pretty straightforward. Discordant and concordant. What the heck does that mean? Well, what's discord? You guys probably know it, and not that thing you guys all talk on. What does it mean to be discordant? Is it good? Is it bad? Bad.
Not working together.
Okay. Discord can be that. I always think about it. I grew up playing bass in orchestra, so I always think of music when I think of discord, right? You hear somebody plays a wrong note, it sticks out like a sore thumb. It's discordant. If your group at work or your friendship is not working, there's this discord. You may not use that word, of course, but there's discord amongst your coworkers. So dis is a bad sort of prefix there. And cordant, well, what the heck does that mean? So what we're essentially saying is, we'll use some carpentry words here. This is with the grain and against the grain. All right? Which one do you think is against the grain? Discord. All right? So the next question is, of course, what is the grain? Well, the grain are the rock layers that are already there. So remember, this igneous material is intruding into some existing rock. It's magma coming up from the mantle into the crust. That rock that's in the crust already has some sort of layering going on, more than likely. So a dike is cutting through that layering instead of going along with the layering. I'm going to show you a picture in a minute. A sill is what they call it when the intrusion goes along with the layering. It is concordant. It goes with the grain. So dikes are against the grain, sills are with the grain. The grain is the layers of bedrock, and as I said, we'll show you a picture in a moment. Lastly, again, the pluton is that pool of magma that's feeding this whole pipeworks. Okay? Or arguably in our next PowerPoint, the pool of magma that's feeding the volcanic event. All right. So, a little fuzzy. I guess it wasn't meant to be enlarged that much. Who remembers what the brick rocks are? Just did that in our last lecture. Limestone, good. And I think that black stuff is supposed to be dashed lines there in the middle, so that's probably some shale. So we've got some magma, the red stuff, intruding into layers of limestone and shale, and then probably we'll say sandstone up at the top since they made it yellow. So those vertical pipes, okay, in this diagram, everything's relative. In this diagram, those vertical pipes would be dikes. When it hits the layers up there with the shale's usually highly fractured. So this stuff is under pressure. It's pushing, squeezing through. Kind of imagine squeezing toothpaste out of a tube or something like that. Okay? And it finds, once you get up into the shale, hey, I could go sideways too, so it starts to spread out. They would call that a sill because it is with the grain. I always think of sills like a windowsill. It's horizontal. But the problem with the catch, as I said, is that's all relative. Because if for whatever reason these rock beds were oriented in a different direction, and the magma still came through in the same way, you might actually A dike might be a sill, and a sill might be a dike. It's all contextually based. It's all in what you see. So it just refers to the orientation of the intrusion compared to the rocks that are already there. I'm always going to keep it simple for you guys. We're going to draw horizontal beds because sedimentary rocks, it's something else I try to reinforce into your head. Sedimentary rocks make horizontal layers. When we get to sed rocks, you'll hear that. So for our diagrams, for our conversational purposes, if you're cutting through there, sort of perpendicularly, if you would, it's a dike. Now, what I was going on about a couple minutes ago about how these aren't technically pipes is that dike or that sill, the sill especially, could go into the board for God knows how long, okay? The sills, it's a lot easier to picture those flattening out and being a layer because, again, that shale, this is a two-dimensional diagram, but you realize that this is a picture of something that goes into the board, behind the board. If you're at home looking at your screen, it goes behind your screen. It's a cube, arguably, at the very least, right? So that crack in the shale is going to be more than just, a pencil's width, so to speak. More than likely, it's going to follow that shale layer for a good ways into the board. So what ends up happening is that magma that made that sill, if we jump ahead into some future and erode all of this away, weather all of this away, and we get down to that shale that you could arguably be walking across going on a hike, that igneous intrusion, that sill, would be something you're walking along. The dike, again, is a lot easier to think of as a pipe, but it too could have some depth to it. All right? It's really easy, a lot easier to picture, I think, with the sills. And similarly, the Pluton, that has depth to it. It's a big old pool, okay? So there's no reason these others can't be, but it's really easy to think of it as a pipe works. Now, in this diagram, of course, it does go all the way to the surface. Conversationally, right now, we're not doing that, but this must have been the best diagram I could find to support my goals. Do not worry about laccoliths and batholiths. You're going to see those in your textbook. We do not need to worry about the size of the Pluton right now, okay? Totally not important to us. But they do classify Plutons based on size and whatnot. We don't care. There you go. Now, driving down the road, you might very well think that that's just a wet section of rock. All right? Because it looks like, hey, you know what, that just got damp. But it obviously caught that guy's attention. And his poor wife's probably standing there on the side of the road. Hurry up, I'm going to get hit by a car. You take your stupid picture. Jackals do that a lot. If you recognize, say, hey, that's actually different rock. Well, that's huge. And it's igneous in that limestone. Oh my gosh, honey, pull over. All right. So, again, going back to, what is that, a dike or a sill, by the way? Oh, it said it on the top. Okay, yeah. Not a hard question, I guess. But it is a dike because, again, the limestone is going horizontally, right? And the some type of igneous that it is cutting straight through it as perpendicular as you can get. But you have zero trouble picturing that has some depth to it, right? It's not just a superficial, or arguably it could be only 2 inches thick, but more than likely it goes way into that rock face. If you were to climb up top where the shrubbery is there, you would probably be able to walk, well, Lord knows how long, okay? But it has some depth to it. Similarly, a sill. It's the dark line towards the bottom.
think that's snow. Is that a joke? I briefly thought it was clouds, and the more I look at it, I'm like, no.
So again, if there is enough magma present and pressure to keep squeezing it, the pipeworks can make its way all the way to the surface, and we find ourselves at a volcanic event. But that, my friends, is for another chapter. Now, if I were smart, because this never really takes the whole time that we need, I would tuck in our conversation about metamorphism here. Because these igneous intrusions are one way that we can get metamorphism. In fact, I am going to take a couple minutes up for it today, just in case we don't get to metamorphic rocks. But in my head, I always talk about them the same way we do them in lab: igneous, sedimentary, and then metamorphic last. But let's go back to... No. You don't need my camera.
Sorry, my PowerPoint was just asking me questions. I don't think it came on the projector here. So let's go back to here. I told you that this was in... well, now I know why I wait on the conversation. This is in limestone, okay? You guys probably don't remember what happens when you metamorphose limestone. Some of you might. So I'll tell you, it turns into marble. That's how we get marble. You bake marble. Well, this intrusion here is hot enough that it can cause that to happen. It's hard to tell in this diagram, but I'd be willing to bet that if you got up really close and looked, that the perimeter around that igneous intrusion there, the limestone has started to turn to some low-grade marble. Now, just like a bonfire, it's hotter right where you, when you're right up close to it. As you get farther away, it cools off. There would be fading on either side of that, to the left and to the right. As you get further away from the intrusion, it would become less and less marble and turn back into limestone. Okay. Different rocks turn into different things. Sandstone turns into quartzite. Shale turns into slate. All right. And one of the ways that can happen is through what we call contact metamorphism, which is where you're literally coming in contact with the hot stuff. All right. So we will more than likely get to that later in the semester, but just in case we don't, this is a great opportunity to at least acknowledge that not only does it leave, cool-looking rock things, but it can cause some rocks to actually change their form. And similarly here, if that was hot enough, you should see quartzite above and below. Up here? What?
No, like right around.
Why it's lighter? Yeah, it could be. It could certainly be. When we talk about temperature metamorphism, we mainly see crystal growth. So that could be taking, let's just say it's a generic quartzy sandstone. It could certainly be making those quartz crystals a little bigger, which would cause them to be slightly more reflective, more shiny, which could cause them to look lighter. But yeah, it's super hard to tell. And I also think metamorphism is far from, it's like going to the podiatrist and asking him about a headache. I know about some of this stuff, but it's certainly not my realm. I have a feeling, too, that temperatures can vary in intrusions, like whether they're fresh versus, they've been intruding for 500 years already. It's starting to really cool off. You might not always get contact metamorphism. Again, at this level, we talk that it always does because we don't want to explain all the shades of gray. But
there's a chance that in like the previous one that there's actually no marble there at all. But conversationally speaking, there certainly could be, and similarly here, there certainly could be some quartzite. But yeah, that's a great thing to notice. It is certainly lighter just above and below that. Well, that could definitely be that could definitely be due to that. All right, so as I said, from here we go into volcanics. This was a chapter, all right? I boiled it down to just under 35 slides, or just over 30 slides, however you want to look at it. There's certainly some stuff in that chapter that I didn't cover. We will not test you on that, all right? Again, I only write questions on what we talk about in here. Please do read the chapter, but sort of don't worry about the stuff that we didn't talk about. If you have questions, excuse me again, goodness. If you have questions about any of the stuff you read and that we didn't talk about, always feel free to ask. I may know, I may not know, but you won't know till you ask. From volcanoes, we take a little side trip and talk about Mount St. Helens, our claim to fame for volcanics in the good old US of A here. And then I quite often wrap up this conversation and give you guys test 2. Okay, I'm going to hit the record, stop the recorder here, because if I should happen to use this in a different semester, I don't want to scare them about test stuff. But